Hi students, so this will be the last of our demo videos. So we're going to be doing geometrical optics and physical optics, especially polarization and diffraction. So I'd like to start by showing you this thing. It's called a light box, and it's really neat for color mixing. So I turn it on. What you'll see is it provides colored light. I'm going to turn off the light here, and let's take a look at what we have. So what we have here is we have red, green, and blue light filters. And as we talked about earlier, even before chapter 24, when we were talking about light in general, we said that the primary additive colors were red, green, and blue. So red, green, and blue light additively make all the colors we know. The primary subtractive colors are cyan, yellow, and magenta, but that applies to pigments. So with this light box, we can see how I've got the colors here. So the primary additive colors, we can see those red, green, blue, but notice where the mixing comes in. So red light mixed with green light gives us yellow light, and then green light mixed with blue light gives us cyan light. And you might be wondering, well, what about magenta? Well, let's take a look at that. To get magenta, we need to mix red light and blue light. So I'm just going to switch a couple of these color filters. Okay, so now you should see here, red light and blue light make magenta light. And we still have the red light and the green light and the red light making yellow light. All right, so that's the color mixing. Now I wanted to show you what happens when we mix all three colors. So if I move the mirrors in, notice how the middle is white. So what we have in this middle strip is we have the mixing of red light, blue light, and green light. And when we put all those colors together, we just get pure white light. And black, of course, is the absence of light. Okay, so that's additive color mixing. Let's do some other interesting things with this light box. And close these mirrors here. And then we're going to put some slits. And so as you can see, we're just getting white light coming in slits through here. And notice what happens if I put a double concave lens. So if I put the double concave lens, we can see the divergent rays there. But we can also see that some of the rays are reflected. Remember, light always reflects off of surfaces. And most of the light goes through the lens, but some of it reflects off it. And we can see those reflected rays are right back here. Those are the rays that we call virtual rays. We call them virtual rays just because those are the traceback rays that our eye interprets. But here, because of that reflection, we can actually see how some faint real rays coincide with those virtual rays right at that point that I'm pointing to right here. That would be the focal point. Now, if I use a double convex, notice here with a double convex that the rays converge, and then the virtual rays, in this case the faint, very faint real rays, which are reflected, we can see those back there. And last thing we'll look at, let me show you the mirrors. So this would be a concave mirror, and as you expect, the concave mirror has the focal point right there. And then I can turn it around to make it convex mirror. And as you see, the convex mirror just reflects all the light. And what I'll show you now is just one slit. And with the large prism here, we're going to see how it produces a rainbow. So let's have this. And you can see right there on the paper how a rainbow is made. This is what Isaac Newton discovered. And what he came up with as the correct explanation of this phenomenon is that white light contains all the colors. And as we know from chapter 23, different colors refract differently, or they refract at different angles. And in rain, all the little water droplets act as many tiny prisms, and that's what produces the rainbows that we look at. But it's all because different colors refract differently. So we see the faint little rainbow here produced by the prism. All right, let's turn that off. Okay, the next thing I want to show you is called a laser refraction tank. And this is a neat device because it's just a tiny tank. You fill it up halfway with water, but it's really useful because you can observe the angles of incidence and refraction directly. All right, so let's look at the angle of incidence. The angle of incidence, here I need to come on the other side. So it looks like the angle of incidence, I can put it to 30. Angle of incidence 30, and it looks like the angle of refraction is about 40. Remember, the angles are measured from the normal, that vertical line. And then I can experiment with different angles. So let's see, this would be an angle of about 40. So an angle of incidence of 40 degrees, but an angle of refraction of 60 degrees. And using Snell's law, n1 sine theta 1 equals n2 sine theta 2, we can remember that n2 for the air is just 1, or we'll treat it as 1. And so if we know the angle of incidence, the angle of refraction, and we know the refractive index of air, we can calculate the refractive index of water. And we could also fill this with other liquids to find their refractive indexes in the same manner. So I like this device because we can clearly see the angle of incidence and angle of refraction, which we can't clearly see in other devices. Now, let's look at another interesting phenomenon. So if I bring this up more, we can see that I'm getting close to the critical angle. And as you remember from chapter 23, the critical angle is where the angle of refraction is 90 degrees. And that's about here. It's hard to get exact, but that's about right there. That's about right there, where the angle of refraction is 90 degrees. And it seems like that's true for water when the angle of incidence is 50 degrees. So 50 degrees is, or appears to be at least, very close to the critical angle for water. Now, the reason the critical angle is interesting is because once you get past it, you get the phenomenon of total internal reflection. And so what that means is that instead of that beam refracting out like it does here, you know, it's refracting out. And even when the beam refracts out, there's always some that reflects in. But once you pass the critical angle, all of the light reflects in and none of it refracts out. And notice that once I pass the critical angle, that just stays true. And we can see from this little reflection down here, that light has simply stayed in the water and come down here. It hasn't left the water. This is the fascinating phenomenon of total internal reflection. And we saw in class that that's why diamonds sparkle, because the water or the light stays trapped in the diamond for many bounces before it finally leaves. This is also how fiber optic cables work, is the light just reflects internally instead of refracting out. Okay. Next thing to show you is an interesting thing called the sunset egg. So, as we learned in, I think it was chapter 22, what we learned is that the reason the sky is blue is because the tiny particles of air act like so many tiny little bells. They get excited with that high energy blue light, and then they scatter that blue light all over the place, and that's why the sky appears blue. So the high frequency blue light scatters effectively. But then what happens is when you have sunset, the light has passed through a lot more atmosphere, and a lot of the blue light or most of the blue light has already scattered out by the time that light reaches your eyes with its longer path through the atmosphere. And so you see it as yellow, orange, and red. Well, the sunset egg works in the same way. Okay, so I'm going to put it close to the light, and you can see what I mean. Okay, so what I'm doing right now is I'm kind of treating that bulb as if it were the sun. And I want you to think of the sunset egg as if it were the sky. And the way that this simulates air molecules is with microscopic glass dye particles. It's called cobalt oxide. And the cobalt oxide particles simulate the action of the air because they behave in the same way. They scatter the blue light very effectively, and notice that the light that passes through, all the way through the sunset egg, has taken a longer path, and that's why that appears yellowish, since the blue light has scattered out. We can also get the same effect if we look directly at it. Okay, so I'm holding it now, and the camera is your eye. Notice that if you look directly at it, you're seeing yellow because the blue light has already scattered out. And I'll do a side view one more time, just so you can see the blue light up here. That would be like the noonday sun, and then yellow light down here. That's the late afternoon, early evening sun. Okay, so sunset egg. It's a good demonstration of the color of the sky. Okay, moving on. We're now going to look at something called the laser ray box. And I like the laser ray box because what it does is it gives you 5 laser beams that are parallel. Okay, now I think I'm going to turn the lights off one more time for this. So the things that we saw with the light box and the parallel slits of white light, we can see similar things with the laser ray box. Okay, so double concave lens. Notice that nice convergence here. Now I'd like you to be looking at this part, okay, not the wall. Look at this part here. Where my finger's pointing, you can see the focal point of this double convex lens right here. It's projecting that right directly onto the table. And then we can see the virtual rays, right? Because light also always reflects off of lenses as well as passes through them. So we can see the virtual rays. In this case, they are just very faint real rays, and those are diverging. Now, interesting thing too is that if you look at the wall now, we can see how the light has passed through all the way. So right, this got bent, went through the focal point, and then reached that spot on the wall. Over here, this beam got bent, went through the focal point, and then reached that spot on the wall. Okay, let's look at the double convex lens. So notice what happens here is the rays diverge. We can see that here on the table. The rays diverge. And then here, the small parts of the light that do get reflected instead of refracted, they reflect at a point here. So they converge on one side and diverge on the other. But we would call these virtual rays in reference to the rays that pass through the lens. And finally, let's just take a quick look at the mirror. Okay, so that would be the convex mirror. We can see how the light just diverges, reflects back divergently, and then here the light reflects back but converges at the focal point. All right, so turn that off. Then I'll turn the lights back on. Okay, so continuing then, we're going to look at this handheld mirror. And it is concave on this side, and it's convex on this side. Convex, concave. And let's just look at it, just, holding it in front of us or at arm's length to see how the different images work. So here's a close-up view. This is the concave side, and then in back the convex side. And you can review the ray diagrams, but we're going to see how this plays out in actual images. So if I hold a concave mirror close to my face, so in this case the camera is right in front of my face, so you're going to pretend the camera itself is my face or your face. In fact, the camera on this phone even looks like a person, 2 eyes and a nose with no mouth. And the white dust around the side there was like some kind of scraggly white stubble. In any case, this concave mirror, when the object is close, such as right now, where the object is in front of the focal point, you get an image that is virtual, enlarged, and upright. So this is the type of mirror that like ladies will use when putting on makeup, or if you have to use a mirror to see something on your face up close, because it magnifies everything that's being seen in the mirror, just as this camera lens is being magnified. Now, this is a virtual image because what we're actually seeing is the virtual rays that converge behind the mirror. But it's larger. Now again, this might be a good thing or a good time for you to review your ray diagram notes, since that will also be part of the test. But the purpose of the demos is so you can see in real life what those ray diagrams mean or what their effects are. So this is an image that is a virtual image. It's also upright and it's enlarged. Okay, now if we bring it farther away, we're going to see how things change. Okay, because we're still seeing something that is virtual and upright, but it's not very enlarged anymore. And then it's going to get blurrier until we reach a point that's beyond the C point or the center of curvature point, such that if you look at anything beyond that point, such as that plate hanging on the wall, right, it's been inverted. So now what you're looking at is an image that is real, not virtual. It's also enlarged to a certain point until, of course, I bring the mirror much farther away, in which case the image would be minified or reduced. But for now, it's slightly enlarged, it's inverted, and it's real. And now you can also see, barely you can see it. Okay, so I'm asking you not to look at what's on the table or my hands or the mirror itself, but what's in the mirror. And you'll see, there it is, you'll see an image of my phone's camera, 2 eyes and a nose, but they've been flipped upside down. That right there is a real, enlarged, and inverted image. Okay, now we're gonna flip it. And now I'm looking at the convex side. Okay, so convex side. The convex side is simple because it's the same every time. What it always shows you, the convex side, is it always shows you an image that is virtual, upright, and minified. Virtual, upright, and minified. So like right now, even though this is close to my phone, it still looks like it's farther away because it's minifying or reducing the image. It is virtual because I am actually seeing virtual rays that converge behind the mirror. So these are all virtual images. They're all minified and they're all upright. So this is also a convex mirror. I literally found this on the road. I was driving along and I just saw it sitting there. I'm sure it fell off of a truck. Here it says, drain hole down. So this must have been mounted on some kind of vehicle. But I found it in the side of the road and I got a free bit of equipment for the science lab. Anyway, I like it because it's a good convex mirror. Remember that when you see images in convex mirrors, they are always upright, virtual, and minified. And that's why having a convex mirror up in the corner is great, like, you know, for security. And I'm sure you've seen this before in like a 7-Eleven or something. Right up there in the corner, you can see everything that's going on in the room. You see a virtual image, but it's upright and it's minified, so everything can fit into that small space. So this next thing I'm going to show you is a solar lighter. And a solar lighter uses the sun to start a little fire. Now, how does it work? Well, what we have is a concave mirror. So the concave mirror, of course, is going to collect the sunlight and bring it all to the focal point, which is here. And so it'll concentrate all that light and heat on the focal point. Okay, so what we have to do is see where the sun is. The sun's right there. We're going to face this directly at the sun and then watch what happens. I'm just going to maneuver it until I get the focal point right where it needs to be. It's fine. There we go. There we go, right there. You can see it smoking because I've got all the sunlight concentrated on that spot, which is the focal point. So this is a cool thing to bring, like camping or something. Of course, it's probably easier for you just to bring a little lighter, but this could be a backup in case you run out of butane for your lighter or something. Anyway, I think it's cool. It's always fun to light things
especially just using the sun. I'm sure you've done that before with a magnifying glass. Using mirrors is actually a little more effective because with lenses, some of the light gets reflected, even though most of it passes through, whereas with mirrors like this one, all of the light gets reflected. None of it passes through. The whole tricky part though is just finding the focus. Well, that's pretty much burnt to a crisp. The next thing I want to show you is a solar panel. So this solar panel is called a photovoltaic cell, and a photovoltaic cell is actually a little sandwich. So if you could look inside there, you'd see what looks like a sandwich. What you have is what they call an N-type semiconductor. Then you have the boundary layer, and then you have a P-type semiconductor. The N-type semiconductor is basically just silicon doped with phosphorus to give it a negative charge. And then the P-type semiconductor underneath would be just silicon doped with boron to give it a positive charge. So you have a negative layer, a positive layer, that sets up an electric field between the two so that the electrons can freely flow through that boundary layer of silicon. And so what happens then is when the sunlight comes in, it frees electrons from that boundary layer that can then move thanks to the electric field. And we can harness that by spinning things. And this is actually a lot more solar panel than we need for a small motor like this. That's why it's spinning like crazy. In fact, it's spinning so fast right now that I'm almost getting that gyroscope effect that we talked about back in chapter 8, where conservation of angular momentum leads to the stability of spinning things. It's kind of hard to spin. But anyway, that's the photovoltaic cell. And these are my solar panels. I've actually got these 7 on one side of the house, and I have another 4 on another side of the house. And together, those 11 panels make all the electricity I need. It's actually really good in the summer months, especially. Sometimes I even make a little extra, and I get paid by the electric company for that extra, which goes back to the grid. But there we have it, photovoltaic cells producing energy as we speak, and good for the environment, and also it saves me a ton of money on my electric bill. That's not true in every county because it depends on who your utility provider is. But where I happen to live in LA County, electricity costs a ton of money, so this ends up saving quite a bit. Polarization. This is a polarizer, and as you learned in chapter 25, a polarizer, what it does is it allows light that's in only one plane to pass through. So it might be vertically polarized or horizontally polarized or at some other angle. So this is a polarizing film, and the neat thing about polarizing films is if you hold them up like that, you can see some light coming through, right? But if you change the orientation, you can get total blockage. Okay, because one of them is allowing only vertical light to get through, the other one only horizontal, and that means when you put them together, you get complete blockage. Now, there's an interesting thing that you can see with polarizing films. So here I have 3 polarizing films. If we put them all together, of course, we're getting light. It's not as intense, of course, because the polarizer blocks some of it. And as we already saw, I can get total blockage. If I turn them a little bit, I'm getting partial blockage, see? So that's no blockage, that's partial. And then notice that when I approach 90 degrees. So there I'm close to 90 degrees. I'm blocking a lot of the light out even more. And then when I hit 90, it's full. So see how there's difference in intensity depending on angle. Now, a really interesting effect though is when you put three together. And if I have them in blockage position, but I put one of these in between, I don't get blockage anymore. I don't get blockage anymore. And this is precisely how LCDs work. Because as you might remember from that animation in the chapter 25 video, what you have is you have in the LCD, you've got a series of crystals that rotate depending on whether a voltage is applied or not. They're acting as polarizing filters. And if I were to just keep gradually twisting things, I would still be able to see light, even though the final one would cause blockage without anything in between it. The fact that when they're not at 90 degrees to each other, some light passes through, means that all that matters is the consecutive angles. So between these two is 45, and then between the next two is 45. That means there's not 90 directly between any layer, and so I don't get complete blockage. In fact, I can put together even more of these, and if I put together a whole series of them, but just gradually turned or changed the angle, I would not get complete blockage. That's an interesting property of polarizing filters, and it's also exactly how those LCD screens work. Now, I'm not going to re-explain here how the LCDs work. You might want to review that if you need to, but this is a cool demo kind of on a larger scale of what is going on in every pixel of an LCD screen. Okay, these are polarized sunglasses. And polarized sunglasses are really good because they cut down a lot on glare, since they're allowing only light in one plane to come through. And this is especially important when you are looking out over water, because water naturally polarizes light, and so this cuts down on all that glare that comes off of the water. That's why fishermen like to use polarized sunglasses. It gets rid of that glare on the water so that they can see into the water, and also it's easier on their eyes. Now there's some pretty cool things you can do with polarized sunglasses just to help us learn better the concept of polarization. I want to show you one here on a computer screen. So take a look at this. If you look through the lens in that orientation, you can see Google. But if you turn it, you get blockage. See? And I'm getting blockage because, remember, the LCD is itself polarized. And so when this axis of polarization is parallel to that of the screens, I get transmission of light. But when the axis of polarization of the sunglasses is perpendicular to the axis of polarization of the screen, I get blocked light, or I get the zero transmission of light. A couple other interesting things with polarized sunglasses. You'll probably want to just do this yourself at home, but if you grab a phone with a screen and you look at that phone while wearing polarized sunglasses, you're going to notice kind of an interesting 3D effect. Almost like there's some depth to the image. And of course that's something that's impossible for me to show you because I can't put the sunglasses on the camera. But because both are polarized, the sunglasses and the screen, you can almost get a 3D effect, because since your eyes are looking at the image through slightly different angles, the axis of polarization is slightly different, making it look like you're seeing a couple of images, one superimposed on the other. And it's not an extremely pronounced effect, not like watching a 3D movie, but
because of polarization, you'll see a little bit of effect when you look at the screen. You kind of hold it at different angles and see how the image changes a bit. That brings me to a brief discussion of how 3D glasses work. Now, I'm not talking about the 3D glasses where one is red and one is blue. Those are called anaglyph 3D glasses. I'm talking about the ones that you can get like when you go see a 3D IMAX, the polarized 3D glasses. And the way those work is that you've got two polarizing filters that are at different axes of polarization. And then the movie itself is actually two images, one superimposed on the other, that were taken at different axes of polarization. So when you put on your 3D glasses, what happens is that one eye is getting one image and the other eye is getting the other image. Thanks to these polarizing filters, it's going to be like on one side blocking what's from one image on the other, but transmitting the other image, and then vice versa on this side. And that's why you can get that 3D illusion, or that perception of depth when you look through 3D glasses. It's all thanks to polarization. Another thing to look at, which you can see, we're talking about LCDs, so this applies to phones. I'm going to put just a tiny bit of water on this phone screen. It's my wife's phone, I better be careful. I don't want to go to the doghouse. Okay, let's see, I'm going to get rid of a little bit of that. Okay, so now I'm going to spread some of this around. And again, this might be something that you can't see very well from where you are. But if you look closely, for example, you look closely at that drop, at this drop here that I'm pointing at, you should be able to see a little bit of rainbow. So I'm going to do it at slightly different, yeah, there you go. Okay, so I'm moving the phone a bit, and then if you see that drop that I'm pointing at, see, you can see some rainbow colors in it. And that's because every pixel on this LCD screen contains red, green, and blue parts. And then different combinations of red, green, and blue make all the colors that we see on the screen. Okay, getting ready to wrap it up. There's not too much to talk about for diffraction, but I am going to show you a few things with diffraction. So as we talked about in chapter 25, diffraction is when light passes through a slit or encounters a barrier, it bends. So it's different from refraction. Refraction is the bending of light as it passes through a transparent material. But diffraction is the bending of light thanks to an obstacle. And the most common type of diffraction that we've studied is the diffraction of light that passes through slits. Now, a really easy example of diffraction, you can do this by yourself now, is if you look at your thumb and forefinger and the tiny space between them, you'll see some fuzziness, and that's because the light passing through that little slit, that little space, is getting diffracted. Here's an example of diffraction. These are called rainbow glasses. So these aren't 3D glasses. I was just holding them for their frame when I was explaining that part. But these are called rainbow glasses because this is a diffraction grating. And what a diffraction grating does is a diffraction grating has tiny little slits, okay? And these tiny little slits let light in, and they block light. So they alternatively let light in and block light. Like a series of, it's as if you have a series of slits like that, you know? But the space between them, between each slit, is much finer. This one, for example, is 500 lines per millimeter. Okay, now if I put these on, I see diffraction rainbows all over the place. It's really cool. Wherever I look at a light, I'm actually seeing rainbows everywhere. And what I'm seeing is diffraction rainbows, not refraction rainbows,
but diffraction rainbows, because light of different wavelengths diffracts differently when passing through a slit. And so it spreads out into a rainbow. Now, I can't put these on the camera, but what I can do is, yeah, there we go. So you're kind of seeing something similar to what I saw when I was looking through these. And notice that when I hold it up to lights, I'm seeing a rainbow. Well, that's a diffraction rainbow. The different wavelengths of light are diffracting at different angles, so that spreads them out into the visible spectrum. Oh, by the way, cool story here. Notice what it says on the sunglasses. Let's see if we can get it there. Manufactured in USA by Rainbow Symphony, which is right in Reseda. Yeah, hopefully it's not too out of focus. Right in Reseda, and you can even call them. You can buy your own rainbow glasses. They have all kinds of other cool optical instruments, but that's not too far from where we live. It's LA area. Okay, so that was one example of diffraction. We've also got single slit and double slit diffraction. So if you look closely, you can see we've got double slit on this side, and then we have different widths of single slit on this side. And we can observe diffraction patterns. All right, so let's first look at double slit diffraction, which was Young's experiment. And remember, Young did this without access to lasers. He just was able to figure out how to make his own little beam of light. But let's look at it with lasers. I'm going to turn off the light. And we're going to see the diffraction pattern, which was an important step to understanding the wave nature of light. I'm going to use red. Okay, so take a look at this. Right, what I'm going to do first is I'm going to pass the red beam through the double slit. And there you go. So against the wall, what you should be able to see, let's see if I can, actually it's better right here. Against the wall, what you should be able to see is a diffraction pattern. The bright fringes are areas of constructive interference, and the dark fringes are areas of destructive interference. In fact, if you bring the camera a little closer to the wall, what we can see, well, we'll get a better view of that diffraction pattern. Okay, so you should be able to see the bright fringes and the dark fringes. Well, as we talked about in the video, that's because with the diffraction, you'll have different angles of arrival at the wall, and depending on those angles of arrival, you could get constructive interference or destructive interference. And we're seeing that reflected here in the bright fringes and the dark fringes. Now, if I go to the single slit pattern, single slit pattern is similar. And this is really interesting because even with a single slit, you're still getting differences in angle of arrival. And this is slightly harder to understand than double slit, because in double slit we can clearly see how light will leave one slit differently from how it leaves the other. But in single slit, light actually leaves one part of the slit differently from how it leaves another part of the slit, and we get a similar diffraction pattern. Okay, now we're going to look at light passing through diffraction grating. So I have, this one is 1,000 lines per millimeter, and this one is 500 lines per millimeter. I'm actually going to use the 500 just because it makes the diffraction pattern narrower and easier to see. All right, so we're going to look at red, green, and blue laser light, and I want you to see if you can notice the difference. Okay, so this is red passing through a diffraction grating.
The brightest one is right in the center, but then look, I have the diffracted ones that are to the right and left of that central one. And this is a diffraction grading pattern. Again, it's all based on constructive and destructive interference. Okay, now let's look at what happens with the green laser. Okay, with the green laser, notice that the spots are closer together. And that's because the green light is higher frequency, shorter wavelength, and therefore it spreads out less when it gets diffracted than the red light does. And if I use a blue laser, which looks purplish, now those spots of constructive interference are even closer to each other than they were with green, again, because this is higher frequency and lower wavelength than the green light. Now, if I put them together, I can see something that almost resembles, not quite a rainbow, but something like it. Notice that now you can really see the difference. They all kind of reach the center, right? But then we can see the spread on either side of that. Notice how closest to the central one would be blue because it diffracts the least, and then green, and then red. And when I look through rainbow glasses, I'm actually seeing this, not with lasers, but with white light, because the different wavelengths diffract at different angles. Okay, well, that wraps up this session of demos. It's been an honor teaching you guys. We've learned a lot of things this year. I really appreciate your cooperation. It's too bad that we didn't see more of each other during the fourth quarter, but of course that was because of something that was was definitely out of our control. Okay, so we did the best we could with what we had. Thanks for your cooperation, and I hope to see you again soon.